Okay, this is the third video on section 2.2, differentials and tangent lines. We worked out all our definitions, what the differential is, what the equation of a tangent line is, and so now I'm just going to work a couple examples. So if I want to know what the differential of, say, ax cubed would be. So notice this d denotes taking the differential, d for differential, and this is my function y. So I want to know what the differential of ax cubed is. So we know that the differential is just the derivative. We could write this way, right? If y equals f of x, then the differential of y is simply f prime of x dx. So we need to know what f prime is to compute the differential. Going to our definition, we know that f prime of x is the standard part of the change in y over the change in x, where change in x is an infinitesimal. And so here our y is ax cubed, so this is going to be the standard part of a times x plus delta x, quantity cubed, minus ax cubed, all divided by delta x. So we'll have to expand this out and simplify. The top is an infinitesimal, the bottom is definitely an infinitesimal, so we can't compute the standard part as of yet, but we can simplify and hopefully get some canceling. So this is the standard part. Expanding this out, and I'm not going to do the gory details. You can either use Pascal's triangle to determine what the coefficients are, or you can just FOIL this out 3 times. But anyways, what you will get when you expand that out is ax cubed plus 3ax squared delta x plus 3, I said squared and didn't write it, 3ax delta x squared plus delta x cubed. So that's the expansion of this, a times quantity x plus delta x cubed, and we'll subtract ax cubed. And the whole thing is still divided by delta x. Now the only thing that we have canceling on the top will be this ax cubed and ax cubed there. And then what's left behind, once those are canceled out, so I'm going to do kind of a few steps at once. Notice I've got a delta x cubed here. I've got a delta x cubed or x squared there and a delta x there. So I've got a common factor of delta x in the numerator, and I've got a delta x in the denominator, so it will cancel out, and which is exactly what we were hoping for. And so this will be the standard part of 3ax squared, because that delta x canceled, plus 3ax. Now I've got a squared, so only one of those canceled, plus delta x squared. And now we can calculate the standard part, because 3x squared is a real number, whereas here we've got our infinitesimals, so the standard part of these two pieces are 0. So finally we can say that the standard part, which is our derivative, is equal to 3ax squared. So then the differential, so kind of putting this off to the side, the differential of ax cubed, we just computed the derivative. So the differential is the derivative, 3ax squared. And then you need the extra term, the differential of x. That is what the differential is. Okay? So the differential of ax cubed is simply 3ax squared dx. Let's take on another example. So let's calculate the differential of the square root of x. So what is the differential of the square root of x? Well, again, to deal with this, we need to figure out what is the derivative of square root of x. So again, I'll do it set up. F of x is equal to square root of x. That's our y. So then f prime of x is the standard part of the change in y over the change in x, which is equal to the standard part of square root of x plus delta x minus square root of x, just by definition, all divided by delta x. And we're in those situations where, again, it's most likely that the difference up here is an infinitesimal. Definitely we're dividing by an infinitesimal, so I cannot calculate the standard part in this form. The square roots are what gets in the way. So how do we get rid of square roots? In this expression, we're going to multiply by the conjugate. That's the only way to get rid of all the square roots in the bottom. We'll get square roots in the denominator, that's fine, but at least we'll get rid of the square roots in the numerator. So this is equal to the standard part of square root of x plus delta x minus square root of x divided by delta x. And then we'll multiply by the conjugate, square root of x plus delta x plus square root of x. But to keep equality, I'm going to have to divide by it again. So I'm really just multiplying by a fancy 1. And so the numerator becomes, we'll have the standard part. The numerator, when we multiply this out, becomes x plus delta x minus x. And the denominator will become delta x times quantity square root of x plus delta x plus square root of x. And so, again, we're going to have some canceling. So this x and this x cancel. And what's left behind is a delta x on the top. And I also have, so this is multiplication here, right? So I have a delta x factor on the bottom. They'll cancel as well. And so what gets left behind is I'll be computing the standard part of 1 over square root of x plus delta x plus square root of x. And now the numerator is a real number, and the denominator I'm not subtracting anymore, so I can slide right through. And this delta x there, it's infinitesimal, so we know its standard part is 0, and so this whole thing, the standard part of 1, and then this slides through, and all that's left behind is x's. So this is equal to 1 over square root of x plus square root of x, or much more naturally, 1 over 2 root x. So that's our derivative. So the question was asking for the differential. So we would write that the differential of the square root of x is equal to the derivative, 1 over 2 root x, times the differential of x. And that is our differential square root x. All right, so that's a couple of examples with differentials. Let's use those same functions to find what the tangent line will be. So for instance, if we're investigating the function, f of x equals ax cubed, we've already shown that its derivative, f prime of x, is 3ax squared. And so if we want to know what is the tangent line at the point, let's say, I don't know, at the point 2, and if x is 2, then y is going to be 8a. So the tangent line at this point to our graph, our formula is y minus f of 2 is equal to f prime of 2 times x minus 2. Notice that the 2's are a repeating factor because that's the x-coordinate. That's really the only thing we need to know. That is the same 2 that's going there, the same 2 that's going into the derivative function, and the same 2 that is being subtracted from x. It's the same point. So our derivative really just depends on what the x value is. And so we can write this out. This is y. F of 2 is 8a. Oops, not equals, but minus 8a is equal, and now f prime of 2, well, f prime is 3ax squared, so f prime of 2 would be 2 squared, 4, times 3, 12, so this is 12a times x minus 2. It's as simple as that. We have a formula, and so it's just plug and chug. And we can leave it in this form. This is point slope form. It's perfectly valid. We could simplify it if we want. For the sake of time, I'm not going to. Let's look at our other function that we computed the derivative of already. So if we let, we're going to consider, what was it, f of x was square root of x. And in that case, we found that f prime of x was 1 over 2 root x. And if we want to know what is the tangent line at the point, say 9. So when x is 9, then y, if I do square root of 9, that's 3. So what is the tangent line at the point 9, 3? So just writing our formula out, we know that it's going to be y minus f of what value? 9 is equal to f prime of what value? 9 times x minus what value? 9. So we're just filling it in, and we know f of 9 is 3, f prime of 9, if we put it into our derivative function, the square root of 9 is 3 times 2 is 6. So evaluating everything here, we get y minus 3 is equal to 1 over 6 times x minus 9. And so this equation is the equation of our tangent line. So that ends this section. There's plenty more examples you can work in the book, and best of luck.